All right. I'd like to, again, begin by thank the organizers for putting together this very nice meeting. Definitely learned a lot. And so I'll be talking about a certain hybrid approach that we've been trying to develop that interfaces cold atoms to mechanical oscillators. In comparison to the other experimental talks you've heard, this is a relatively young effort. We've only been working at this for about 6 months. So I'll try to explain the motivation and the progress we made in that time. So I mean, one of the perks of going speaking on the last day is that I can gloss over the motivations that have been mentioned already many times. But I'll just say that one of the things that, as atomic physicists, that I've really taken away from this really nice work by all these groups on micromechanical oscillators, like Cleland's work or John Teufel's talk yesterday, is that as important as the mechanics is, it's also very important to interface these mechanics with some very tunable auxiliary quantum system, whether that be a Josephson qubit or a nitrogen vacancy diamond magnetometer. What we are trying to do is to interface these oscillators with cold atoms, because from my perspective, a cold gas gives me a very tunable mesoscopic quantum system with a well-established toolbox of probing and addressing, which I can use to confine very close to the mechanical oscillator and try to get at some of the physics that I've outlined here. So I was first interested in doing this purely from a quantum sensing perspective. So cold gases are great quantum sensors, but of course for various reasons they suffer as you go to smaller and smaller dimensions. So can we get something? Can we gain something by interfacing these cold gases to micromechanical oscillators or nanomechanical oscillators? And of special interest to me is the whole idea of magnetic microscopy at very short length scales. Okay. So just a very brief review. This probably is fairly obvious to most of the audience, but just to set the stage, if you were to say how exactly would you measure magnetic fields with the atomic gas, the idea is very simple. You start out with a spin polarized medium, which you then put in a superposition of, say, upspin and downspin and if this spin is oriented in a plane that's transverse to the ambient magnetic field, then obviously the spin is going to undergo Larmor precession at a rate that's essentially linearly proportional to the magnetic field. And so then estimation of the magnetic field in the system just amounts to a very accurate measurement of the Larmor precession frequency. And this is usually done by optical means. What I just said works very well for thermal gases. And there's a very long established tradition of using thermal vapor magnetometers, which I think, as far as I know, to date, are among the most sensitive magnetic field sensors out there, with sensitivities approaching a femtotesla per root hertz. So why exactly do we use cold gases? There are various reasons, and more of these reasons will come about as I go further through the talk. But one of the things is that, from my perspective, a cold gas is something that's very easily, that I can manipulate, confine rather easily, very close to surfaces, and get the spatial resolution that a thermal gas does not allow me to get. Okay, so if I'm looking to map out or do magnetic microscopy at very short length scales, say micron length scales, then what I really want is a gas which doesn't, by virtue of its temperature, that really does not move much on those length scales during the time of my measurement. And the other aspect that we use here is, I said the measurement of the Larmor precession is usually done by optical means. So just to elaborate on that statement, what we typically use is the fact that these spins, when coupled to polarized light, exhibit either linear or circular birefringence. So I'll be working not with, in contrast to the diamond vacancy, talk about the diamond vacancies or the nitrogen vacancies we heard yesterday. The atoms I'll be using are not spin 1/2 systems, rather they're spin 1 systems, which means that there's a slightly there's some techniques which extend or are common to both these systems, but there's some techniques which are peculiar to the fact that we're using a spin 1 system. So in particular, the fact that we have a spin 1 ground state means that the phase contrast signal or the Larmor precession signals that we get take this form where there's both a linear part, there's a signal which is, there's a contribution to the signal that's proportional to the projection of the spin along the probe axis, but there's also a quadratic term. This small quadratic term will start playing a role when we start talking about continuous quantum measurements of the system. But in brief, what you can see is that if you look at the Klipsch-Gordon coefficients outlined here, what you can see is that if the spins were polarized along this probe, then the gas for a sufficiently far off resonant probe would exert a phase shift which is proportional to the square of this Klipsch-Gordon coefficient. In contrast, if the spins were aligned or anti-aligned with respect to the probe, they would the atomic gas would cast or imprint a phase shift on the probe which is proportional to the square of this coefficient. So what would really happen as the spins, if the spins were to Larmor precess, is that the phase contrast signal that you would perceive oscillates between the maximum of this value to a minimum of this value. And so if you were to create a spin which transfers the magnetic field, and the spin on this Bloch sphere undergoes Larmor precession, then what you would do to extract a time-resolved map of the Larmor precession is to strobe a far-off resonant probe aligned along the y-axis, so that as during the Larmor precession, as the Larmor precession ensues, the orientation between the spin and the Larmor and the probe oscillates at the Larmor precession frequency. And so, if you were to take many images of the same gas, what you would see is as a function of time, you would see images where the Larmor precession or the phase contrast signal of the Bose condensate oscillates in time. This was a technique that was pioneered by Stamper-Kurn's group at Berkeley, and it's actually a very neat technique, especially from the point of view of magnetic microscopy, because what you can do here is to make use of the fact that the Bose condensate is a spatially extended gas, and if you're trying to measure the magnetic field or map the magnetic field of a localized region somewhere here, you can make use of the fact that the atoms very far from what you're trying to measure constitute a very good measurement of the ambient magnetic field. So if I were to take the Larmor precession phase of regions, say far from the region of interest out here, I would get a oscillatory signal as a function of time, and then all I need to do is to compare the phase of this oscillation to the phase of the oscillation or phase of Larmor precession of some region which is closer to my region of interest. So in this movie, I'm showing essentially a condensate that's precessing under a very uniform field. So there's really not much interesting that's going on out here. So the phases, as you can see, are almost exactly the same. But you could also choose to do this in a case where the magnetic field along the condensate is not uniform, but rather has a localized feature, in which case you would see Larmor precession movies that look like this, where the central region is distinctly out of phase from regions far from the center. And so if you were now to look at the phase difference between regions close to the center where there is some magnetic inhomogeneity to regions far away, then you can use that phase information to extract either a 1D or a 2D map of the magnetic field. So obviously, when you have a technique like this, where you can say I am sensitive to some field, the obvious question to ask is what is the sensitivity? What are the limits? So we are trying to measure the magnetic field perceived by the atoms by an optical means, which means that we are limited, or there's a limit imposed both by atom short noise and by photon short noise. And if you go through the calculations, what you can see is that the photon short noise as part of the sensitivity limit has both a linear part because of spin depolarization as well as a quadratic part on account of the fact that the atoms are Bose condensed and they have a tendency to superradiate. But you can find, the upshot of this slide essentially is that you can find regimes of the probe detuning and the fluence and so on, where you're limited mostly by the atom short noise. Okay. At very low fluence, or if you shine very little light on the condensate, obviously your dominant term in the sensitivity is going to be photon short noise. At very large intensities, on the other hand, here the light is essentially going to depolarize the condensate, again giving you an increased noise. But somewhere in between, you can find regimes where the this magnetometer is purely limited by atom short noise. And at the atom short noise limit, if you look at the field sensitivity, what you find is that the field sensitivity is a few orders of magnitude better than, at least for the spatial length scales that we are interested in. This condensate magnetometer is actually much better than the existing technologies, of which squid sensors are normally perceived to be among the best magnetic sensors at length scales of a few microns, and what you see is that the BEC is actually much better than that. So if it's all that, I mean, so what I've basically told you is that in principle, the Bose condensate is an extremely good magnetic field sensor, and so and the idea is, can we now use this magnetic sensor to interface with mechanical devices, or what are the possible applications? But before we get to that part, of course, we have to say, metrology with cold gases has been a very long-standing kind of. Is something that people have been wanting to do for a very long time, and there have been very few experiments or studies of metrological measurements with quantum degenerate gases, which have challenged the state of the art. So what are the problems there? On the one hand, we have there are lots of advantages to using Bose condensed gases or degenerate Fermi gases. So for instance, they're very easy to manipulate and control. They have a very long coherence time. They're in an interacting many-body system, which then obviously raises the prospects of creating non-classical correlations and so on. On the other hand, the creation of Bose condensates comes with a fair amount of technical challenges. So in terms of metrology, the duty cycle tends to be very low. It takes a very long time to create a Bose condensate. The measurement is then the actual measurement time is a small fraction of the time it takes to create a Bose condensate and so on. And partly because of that, there are various technical challenges as well. You need very good vacuum and so on. The short answer is it can last many seconds, but I'll get into a little more detail on what determines that later. But how long does the condensate last? It's a combination of how good your vacuum is and the density of the gas. So how good your vacuum is, because hot atoms in the background keep kicking out the condensed atoms. But even in the absence of that, if the density is pretty high, then you have what's known as three-body loss. That's essentially the onset of a molecule formation and so on. So if you combine those two, for typical densities that we work with, that lifetime is on the order of a few seconds to tens of seconds. So in terms of the cons, I would say call these the technical challenges to creating a metrological resource with quantum degenerate gases. There are also fundamental challenges. Because it's a fairly strongly interacting many-body system, you also have to take into account density-dependent shifts, which usually are uncontrolled systematic. So in terms of the technical challenges, a lot of these can be alleviated if you just came up with ways in which to create Bose condensates very rapidly. So very rapidly, as it makes things more robust. Your duty cycle goes up. The technical challenges or the technical requirements, such as very good vacuum, are relaxed a lot. For the specific case of metrology or magnetic field measurements with spinor gases, it just turns out that if you use the right kind of Bose condensate, in other words, a ferromagnetic spinor condensate, because of the fact that spin is conserved in these systems, it turns out that there is no mean field shift to the Larmor precision frequency, which is the quantity you're actually trying to measure. So put another way, because of spin conservation, if I were to take a ferromagnetic Bose condensate and look at its Larmor precision, it turns out to be exactly the same as the Larmor precision frequency of a single atom. which then means that you have the benefit of bosonic stimulation. You have a lot of atoms to work with without the associated density dependent shifts. This is something that's peculiar to this specific measurement, the measurement of a magnetic field with a spinor gas. So it's not a very general statement. But as far as we are concerned, we don't have to worry about the main field interaction. Okay. So assuming those technical challenges can be alleviated, then essentially what we have is a very, very good spatially resolved magnetic field sensor. And so there are a fair number of applications that we had in mind. The first, of course, in a kind of trying to chart out a scientific program, we got interested in being able to use the sensitivity of the cold gas to detect the micromotion of a mechanical oscillator. So the idea was, can we confine a spinor Bose condensate very close to a mechanical oscillator and then detect the motion of this oscillator with the condensate? And that being a first step to then doing more interesting things, such as maybe sympathetically cooling the oscillator with the cold gas, trying to transfer non-classical correlations from the Bose condensate to the oscillator and so on. As a first step, we start asking the question, well, how sensitive is this, and can this condensate, given its sensitivity, detect the micromotion of a Bose condensate? First of all, micromotion of an oscillator. So how would you actually couple the two? So the simplest scheme we came up with is actually rather similar to the scheme we heard about from Misha Lukin's group yesterday. It's a cantilever or a membrane in our case with a small microdomain deposited on the membrane. And this small domain, by virtue of its size and large surface field, exerts a fairly large gradient in its vicinity. And so as this membrane moves around, the Zeeman energy or the Zeeman shift at the location of the condensate changes. And so then you can write down a coupling term which is just proportional to the gradient times the small displacement of the and these were the kind of typical numbers that we were aiming for in the experiment. The nice thing about this geometry is that with just changing, if you're free to choose or deposit different kinds of domains on the oscillator, then you can also go from something that's linear in the displacement to something that's quadratic in the displacement, just by using the symmetry of the magnets. So if you were to use two magnets anti-aligned in this configuration, then what you have is something that approximates, at least in the for certain regimes of operation, which approximates a quadratic coupling. So given the kind of multiple things that had to work right, we kind of divided up the whole effort and said, okay, first of all, we have to build a BEC machine where we can actually confine Bose condensate very, very close to micromechanical devices. We had to find ways of creating Bose condensates very, very rapidly. There's also the fabrication challenges to creating these oscillators with very large mechanical quality factors, which at the same time are also capable of generating large gradients with small domains on them. And lastly, the whole theoretical formulation of how exactly does the measurement work? Either a single measurement of trying to discern the micromotion of the oscillator, or can we develop that further and start thinking of continuous quantum measurement and how that would then change the evolution of the oscillator. So if you were to just look at the kind of very naive back of the envelope calculations and say if we were to take an oscillator or a membrane of mass of picogram and roughly oscillation frequencies on the order of hertz, the 0 point motion is on the order of 13 femtometers. And so if you now were to couple this magnetically to the oscillator, to the condensate, does the condensate have a sensitivity that allows you to actually be able to measure the small displacement? And it turns out that if you have a domain which can generate a gradient of roughly a Tesla per meter at the location of the condensate, then given our field sensitivities, we can actually, it should be feasible to detect the micromotion within around 1 second of integration time. So these back of the envelope calculations seem to suggest that we are not orders of magnitude away from what we are trying to do. So then, as an experimentalist, my next approach was to just ask the nearest theorist, who in this case happened to be Pierre Meystre. And so his group started taking on the challenge of addressing or trying to come up with a rather nice formalism for how exactly the oscillator would couple to the condensate, both in terms of projective measurements and in terms of continuous measurements on the condensate, and whether so for a linear coupling, that measurement of the oscillator position should then result in a back action on which in principle we should be able to measure. And that would be, to me, that's rather neat, because now we're talking about quantum back action on a object that's tens of microns large. So I don't want to go too much into this because that would be one of the things that Swati will be talking about right after me. So this is meant more as a advertisement for you to stick around. So that's as far as the theoretical part of the program. The other aspects of the experiment, are, of course, trying to come up with a machine where we can actually do this experiment. So this is this is the design for the BC chamber that we have. It's actually a very compact, simple design for a BC chamber. Essentially, we collect or pre-cool atoms in what we call a primary glass cell, push them over to this chamber, which has a flange which can be cryogenically cooled, which houses the micromechanical oscillator, and the condensate will be confined within a few microns of this oscillator right there. And that's to go from SolidWorks to reality. That's what it is. Okay. So the timeline of this, of course, we got the tables in July. The theorist was there to make sure we installed it right. And then the usual work that's involved in getting a BC machine in terms of the UHV chamber, the lasers, the oscillators, which we had to go through a few iterations for in terms of fabrication, and so on. And so by December, we were in position to get the characterize the last generation of the second generation of the micromechanical devices. We saw that the quality factors we were getting were on the order of 10 to the 6, which is more than what we expected. The next challenge, of course, was to say there's this very tiny micron-sized domain somewhere in the on this device, and we need to map out the magnetic field of this micron-sized device. And the best way to me of doing that was to just introduce this into the vacuum chamber, create a Bose condensate on top of the membrane, and then use the condensate to map out that. The other aspect of it was, I said, it would be very nice, especially for metrological purposes, to come up with ways to create Bose condensates very, very rapidly. So if you say, well, what is the hold up? Why is it so hard? So the usual way of creating Bose condensates is to start out with some, say, in this case, start out with rubidium vapor, and then go through a few stages of pre-cooling, which is mostly optical cooling, which still, in terms of phase-space density, is pretty far away from degeneracy. So with very, very good optical cooling, or at least very, very good Doppler cooling, you can be at a phase-space density of maybe around 10 to the minus 5, 10 to the minus 4, which is still a fairly large distance away from actually getting the beams. That intermediate span is usually covered by something called evaporative cooling, where you let the atoms collide, and then the hottest atoms leave the trap, and the remaining atoms then have to rethermalize, establishing a lower temperature. And you continuously do this until you get a BEC. The downside of this process is that this evaporative cooling, optical cooling, is very, very fast, works on a time scale of milliseconds, and it's free in the sense that you don't lose atoms. Evaporative cooling, on the other hand, is collision limited. These are dilute gases, so the collision timescales are on the order of seconds, and it's expensive in the sense that in going from a phase-space density of around 10 to the minus 5 to a phase-space density of 1, you lose about 99.9% of your atoms. So the approach we took was to say we're going to try to get as close to BC just by optical. And so the technique that we had in mind was something called Raman sideband cooling, which is pioneered by the group of Steve Chu. So now the challenge here was to not just re-implement this, but also optimize this for much larger atomic ensembles than it had been done before. So to kind of draw a comparison between sideband cooling as applied to atoms to the forms of sideband cooling or resolved sideband cooling that the micromechanics community is used to, or even the ion community is used to. What you really need. So here, I mean, you use the fact that or use the you drive the system to the red, and then use the fact that the oscillator response creates a asymmetry between the Stokes and anti-Stokes process. But what you really need for this to work is that you want a trap which is tightly enough confining that the trap frequencies are resolved with respect to the natural line widths you have. Okay, so for neutral atoms, on the natural line width of the electronic transitions is on the order of a few megahertz, and it's very hard to come up with traps which have trap frequencies that large. So what one of the insights that Steve Chu's group had a while ago was that instead of using the ground and electronic states, what we can actually use are metastable states of the ground states. The atoms have internal structure. So if you instead use metastable states within the ground state manifold, then the line widths, the natural line widths of those transitions can actually be much more narrow, which means that even kind of traps whose trap frequencies are on the order of 100 kilohertz are still sufficient for you to get into this resolved sideband. So to illustrate this process, just for a spin 1/2 system, the way you confine the atoms in what's known as an optical lattice, and the optical lattice for sufficiently large detuning is independent of the spin state. So the potential looks the same whether the atoms are in the plus 1/2 state or the minus 1/2 state. And so then if you then apply an ambient magnetic field, you shift the two potentials with respect to each other, and you can shift them in such a way that the Zeeman shift is exactly equal to the trap spacing. In this case, you then you then create a two-photon coupling between states which differ by one vibrational level. This is still a purely coherent process, so as by definition it cannot cool. So what you need is to have some kind of an optical pumping process, which then brings you back into the high field sequence state. The key is that in this process, as the atom absorbs a photon and then emits a spontaneous photon into the vacuum, it goes into a state whose vibrational level is the same as the one before. And the reason this happens is that the atoms are tightly enough confined that they are in the lambda key regime. So the probability of inelastic processes is actually fairly low. So as you keep doing this, you can see that at some point the atoms will get optically pumped and cooled into this state, which is a dark state in the sense that it does not have a partner to couple to. And so as this process continues, what you'll find is that the temperature reduces by virtue of the fact that the atoms keep losing one vibrational quantum, and once they get to this ground state, they switch off in the sense that they don't see the light anymore. So this is as far as a spin 1/2 system is concerned. Like I mentioned earlier, we are working with a spin 1 system, but the process, in a sense, works very similar. So this is the geometry we used. This is more for the experimentalist audience. We have a vertical lattice with some so we had to work a bit or think a bit about how to do this for extremely large ensembles, and by extremely large I mean many billions of atoms. But we got that to work, and so these are values which I can address again if there are questions. But at the end of the day, the most striking demonstration is actually looking at the images. The way we measure the temperature, of course, is to release the atoms from the trap and then let them expand and see. After sufficiently long times of flight, the spatial distribution of the gas is a very accurate reflection of the momentum distribution in the trap. And so, by looking at how fast the gas expands, you can extract the temperature. And this is for this set of time of flight images is for the initial phase of the gas. So it's at a temperature of around 100 microkelvin and a phase space that's -6, which is typical of of this stage of Doppler cooling. Okay. And so maybe 10 milliseconds later, after this Raman sideband cooling process, we capture about half the atoms from the MOT in the lattice, And you can see just visually by the time of flight imaging that the atoms are actually much, much colder. And so this is actually, so in 10 milliseconds following this stage, we've gone to a temperature of, we've gone from 100 microkelvin to a temperature of slightly less than a microkelvin. And phase-based STS correspondingly improved. And following this, we immediately load the atoms into a far-off resonant trap, and then we can evaporate that down to BEC. We're already very, very close to BEC, so this process actually takes should take a very, very short amount of time. So just to summarize, this is kind of the recipe that we've been following, is to create or pre-cool a very large ensemble of atoms, and then after some stages of compression and so on, subject these atoms to Raman sideband cooling, which causes the base phase density to jump up really, really rapidly with minimal loss of atoms, and then transfer those atoms into a far-off resonant optical trap and then evaporate to BEC. The idea being that we can actually make this process work in less than a second. The other aspect of the work was to come up with a very good oscillator with very quality quality factors, and that it took us a few tries to get that, but the upshot at the end of the day was that that also is actually working as of last week. This is so for a little more on the fabrication. It's a stretched silicon nitride membrane, and that's right now the domain on the membrane is just soft iron, which can be polarized with a large enough field. But we have to talk a bit more, or we have to discuss a bit more and see. Once we have accurate measurements of the magnetic field around this domain, we can go on to using maybe there are better materials out there which will give us larger gradients. But for now, the mechanical quality factors are actually this is all. Here we have we measured a mechanical quality factor larger than 3 times 10 to the 5, but it's almost certainly vacuum limited because this was at a pressure of a millibar. And as far as we could tell, as the pressure decreased in the chamber, the quality factor kept decreasing, and I don't think we've saturated yet. So it could very well be the case that this membrane here has the quality factor greater than this. The next challenge, of course, is to now use the cold gas to map out accurately the field of this membrane, make sure that it has the gradients that we need, because that's the key. Along with the quality factor, the gradient is key to getting this mission, getting this experiment to work. So with that, I'll just summarize. We started going along this track because it seemed to me that spinor Bose-Conseil is by far one of the most accurate magnetic field sensors out there, and the idea was to try and couple this very, very accurate device to a micromechanical oscillator, both to probe its motion, but also at some point, hopefully in the near future, try and find ways of cooling the oscillator or transferring non-classical correlations from the Bose-Conseil into the oscillator. And so this, there have been a bunch of things that we had to get to work in that process, and a few of those have been working rather well. And with that, so I also want to thank my collaborators, a great bunch of students at Cornell. Dave Brown and Pete Schwab have helped us a lot with the fabrication of this device. And as far as the theory work is concerned, Swati and Steve have really led the way there on the theory front. And Swati will be actually speaking right after this.